This is our second example for beam design, in which we will be covering the bending moment and shear and deflection. Because the first example we only designed the beam for bending and we stopped, but in this example we'll have this beam designed for bending and check for shear and deflection. So if you look at this example here, you see this says design a wood section for wood section for the following beam, case and loading, and it's given the maximum allowable bending stress FB equal to 1350 and maximum allowable shear stress FV is 850 pound per square inch, and the modulus of elasticity E is equal to 1.6 multiplied by 10 to the power of 6 psi, or pound per square inch. And by the way, psi, pound per inch square, means psi. So just in case we see psi, that is the meaning of this. And maximum allowable deflection is given as L by 180. L is the span for the beam. In this case, the span is 10 feet. So let's start. The first step number one is we need to calculate the maximum bending moment. And as you see, we have a case of cantilever with uniform distributed load 250, and we have point load at the end was 550 pounds. So this is a case of two. So if you look at your schedule, your table charts, you see we need to go and look for a cantilever beam with uniform load, which is case number 19 here, as you see. And the maximum bending moment is given here as WL squared divided by 2, and maximum shear is WL, and maximum deflection is given as this. That is case number 19 for uniform distributed load. And the other case is point load at the end of the cantilever, which is case number, let's see, this is case number 22. So it says it is a cantilever beam concentrated at the end, and you have maximum bending moment is PL, maximum shear is P, and maximum deflection is given as PLQ divided by E. So this is where you get your equations from. Okay, so now we move to break down this beam into these two cases. So if you look at how we do that, we have the following. So we have the beam itself here is equal to the uniform distributed load 250 cantilever and point load cantilever. So this is how we calculate that, and the equations, we take these equations from the chart, and as you see, the bending moment we have WL squared divided by 2 for bending moment for the uniform distributed load, and for the point load it is PL. And then if you go back to the chart, you have to put the chart in front of you to be able to understand. And then the shear for the uniform load is WL, and the point load shear is only P. For the deflection part, the uniform load will be WL to the power 4 by EI. I means moment of inertia, and this is properties of a section that you can get from the table. And for point load, the deflection is PLQ divided by 3 EI. Okay, so with this we will move on to go with the normal steps that we normally did, and as we start by step number one. Step number one is to calculate the maximum bending moment. And this bending moment M is composed of WL squared divided by 2. That's for the uniform distributed load cantilever, and for the point load cantilever it is equal to P multiplied by L. So there's two parts. Now if you go back to if you look at the diagram here, you will see the W or omega is equal to 250 pound per foot, multiplied L is 10 feet squared divided by 2, plus P is given as 5 50 pounds multiplied by the length, which is equal to 10 feet. So if you have the units here, of course we have to do unit math here. This becomes foot square, and then you do the cancellation of this foot square with this foot, so you'll get pound foot, and for this part it is pound foot already. So I mean we are consistent in our addition. So if you go to the numbers now, this should be equal to is equal to 12,500 pound foot plus 5,500 pound foot. So M total is equal to 18,000 pound dot foot. This is the first step, which we did in the previous example also. Now step number two. Step number two always is, step number two is to calculate the section modulus value, and we do this from the equation which is FB, and this is actually given in the module 8 explanation is equal to moment divided by Sx, and from this we get Sx is equal to moment divided by FB. Just you need to watch for the units, because the units might be sometimes a problem. So for Sx, and Sx value is, if you look at the tables, you'll see it is an inch to the power of 3, so you need to get this value in an inch to the power of 3 to be able to select a section. So the moment is 18,000 pound, that's pound foot, divided by FB is given as in the question as 1350, so it is equal to 1350. It is pound per inch square. See, there's a, we always do the cancellation of units and then we do the conversion. So see if there's any cancellation. In this case we do have pound, and pound will be cancelled out, but you will have foot and inches here, so we need to make some sort of conversion here, and the conversion normally for Sx we have to convert everything into inches, so always we need to convert this into inches. So I need to get this feet into inches, and I do that by multiplying by 12. So now this is equal to, so I get here a value for Sx equal to 160 inch to the power 3. Just in case if you're wondering how we get inch cube, because this inch square goes up and becomes multiplied by inch, becomes inch cube. So that is the value of the section modulus. So I need a section modulus. I need a section that has section modulus of 160 or more. So now you go back to the tables to be able to select a section. So if you go through wood tables, which will be the first tables by the way, here, so I'm looking at an Sx value here. This is Sx value, and I find the closest to 160 is 167, and that is section 6 by 14. So 6 by 14 inch will give me a section modulus of 167, and it gives me an area of 74.25 and moment of inertia of 11.27. These values I need because I will have to put them, so I will, let me just put them one at a time. So I say use step number 3, of course. So step number 3 will be, so I'll move to step number 3. Let's get this done, and so step number 3 is choose a section. In this case I have chosen beam 6 inch by 14 inch, and this beam will give me an SX value equal 167 inch to the power of 3, which is greater than what I calculated, and I calculated 160 inch cubic. And of course I have to get the other values. The area is equal to 70, let me just again double check, it is 7425. So it is 7425 inch square, and I need the moment of inertia value, which is equal to 1127.7. 1127.7, that is inch to the power of 4. So this is what I need from the section. Now this is familiar so far because we did this before in the previous. Now what we will add here is step number 4 is to check for shear stress. So step number 4 is check for shear stress. And we have an equation for wood. Shear stress V is equal to 1.5 V, which is the shear force, divided by the cross-sectional area. This is an equation, and you find this in the template, and you're allowed to bring this template with you to the test if you want to. So the step number I need to calculate here, calculate the shear force, which is V. And to calculate the shear force, again, if you go back to the template here, back, shear is WL for the uniform load, and it is P for the point load. So again, back, so V is equal to WL plus P. W is equal to 250 pound per foot, multiplied by L is 10 feet. That is the first part, and the second part is P, which is equal to 550 pounds. And again, you see the units are pounds, so if you do the cancellation, foot and foot will be cancelled out. You'll be left with pounds on this side, and it is pounds already on this side. So see what this number is equal to. So is equal to 2500 plus 550, and is equal to 3005 pounds. So that is the shear force. Now we need to calculate the shear stress and compare it to the maximum allowable shear stress. So this shear stress V stands for the actual shear stress. So we need to do actual shear stress calculation, and is equal to 1.5 but the shear force is equal to 3050 pounds. Again, we care about the units here not to make mistakes. And the area, we did get the area here, the area is from the table is equal to 74. So 74.25, it is inch square. So if you look at the outcome of this calculation will be pound per inch square. So that is good. So is equal to, the result for this is equal to 61.6, that is pound per inch square. So we need to compare this value. This is the actual shear stress. We need to compare this to the maximum allowable shear stress, which is given in the question. So if you go to the question itself, so you see the maximum allowable shear stress is given as 850 pound per square inch. So let's go back to our calculation. So this is less than 85 pound per inch square. There's a typo. The question has the maximum allowable shear stress is equal to 85 and is not 850 per inch square, because this is typo. There's a typo here. Okay, so this means it passed. Now the last part is to calculate the deflections. So step number 5 is calculate the actual deflection and compare it to maximum allowable deflection, which is L by 180. So let's do the L by 180. So L is the span, and the span is 10 feet. Divide by 180, and always we measure the deflection in inches, not in feet, so we need to convert this into inches. So multiply by 12 always, and that's how much is maximum allowable deflection we get for this cantilever beam, which is 10 multiplied by 12 is equal, divide by 180 is equal to, so is equal to 0.67 is maximum allowable deflection. Now again, to get the value for the deflections is I need to go to the chart. So if you look at the charts here on page 2, so it says the maximum deflection for uniform load is this much. For the uniform load is WL to the power of 4 divided by EI, and for point load is equal to PL cubed divided by 3 EI. So I need to write these down and start to work on the numbers. So let's tab new page, I guess. That's fine. That is page 5. Okay, so I'll put the equation here. So we have the total deflection is equal to uniform distributed load is equal to WL to the power of 4 divided by 8 EI, and for point load is equal to PL cubed divided by 3 EI. So let's do this. You do this very carefully because there are lots of units here. So the W is equal to 250 pound per foot, multiplied by the span is equal to 10 feet, that is to the power of 4, and divide by 8, multiplied by the modulus of elasticity is given as 1.6 multiplied by 10 to the power of 6 pound per inch square, and the moment of inertia is from the table is equal to 1127.7 inch to the power of 4. So that is the first part. Now the second part is P is equal to 550 pounds multiplied by L is 10 feet cubed, and divide by same by 3, multiplied by E is equal 1.6 multiplied by 10 to the power of 6 pound per inch square, multiplied by 1127.7 inch to the power of 4. So as we have always said, we need first of all to do the cancellation of units and then do the conversion. So if you look at the chances for us to do the cancellation, we have the pound, and the pound will be cancelled out. Inch square and inch to the power of 4 becomes inch square, and same thing goes for this part. We have pound and pound will be cancelled out. Inch square and inch to the power of 4 becomes inch to the power of 2. Now this part, the unit becomes foot to the power of 4, and this one becomes foot to the power of 3. Now we do the cancellation here, so we have foot to the power of 4 foot, so this becomes foot to the power of 3, and here on this side we don't have any cancellation, so that is fine. So now if you look at now with the units here, you see we have inch square here and we have foot cube here. We have inch square here and foot cube here. So we need to be consistent, so we need to do conversion now. So I need to convert this foot into inches. I have to convert this into inch cube, and I do that by multiplying by 12 to the power of 3. And I need to convert this into inch cube, so I multiply by 12 to the power of 3. You should do this to be able to get the right answers. And if you do these numbers, then this will be equal to, you see, is equal to, this will be 0.299 inch square plus 0.175 inch square. And now if you add these up to, so 0.299 plus 0.175 is equal to, so we get a value equals 0.474 inches. Now we need to compare. This is the actual deflection. This is the actual deflection. I need to compare this to the maximum allowable deflection, which I calculated on page 4. So the maximum allowable deflection is 0.67. so let's go back to 0.67. so this is less than 0.67 inch, so meaning the actual deflection is less than the maximum allowable deflection. So that means the design is okay. That is the end of this example. You need to go through these examples again and practice and see if you have any questions. Hopefully I will answer them in class.